Okay. The first part says find two square roots of the complex number minus 3 plus 4 iota. Okay. So what we do is we write square root of minus 3 plus 4 iota would also be equals to a complex number. Let's call it x plus iota y. Square both sides. So minus 3 plus 4 iota equals x plus iota y whole squared. Use the identity a squared plus 2ab plus b squared. Iota y whole squared would be minus y squared because iota square is -1. So this would be minus y squared equals minus 3 plus 4 iota. Let's equate the real parts. So minus 3 would be equals to x square minus y square, and equate the complex parts. So 4 equals 2xy. Okay. Now we're going to use substitution. So we can say let y equals 2 upon x. Okay, now substitute it here. Minus 3 equals x squared minus 2 upon x whole squared, which gives us minus 3 equals x power 4 minus 4 upon x squared, which gives us minus 3x squared equals x power 4 minus 4. Rearrange and we get x power 4 plus 3x squared minus 4. Okay. We can use hidden quadratic equations here. 0 equals x power 4, and we could use plus 4x squared minus x squared, that's middle term breaking, minus 4. Take x square common, so x square plus 4. Take -1 common, x square plus 4. 0 equals x squared minus 1 and x squared plus 4. Okay. So we're getting x squared equals 1, or x equals plus minus square root of 1, which is just 1. So plus minus 1. And for the other one, we don't get any real roots, so no real solution. Remember this x and y here, both of them need to be real. That's why this one will not give a real answer and we reject it. So now let's find both the values of y. So when x is 1, y will be equals to 2 upon 1. So 2. And when x is -1, y will be equals to -2. So our two roots are 1 plus 2 iota and -1 minus 2 iota. Okay. That's the answer for part A. Part B. The complex number u is given by 7 plus 4 iota upon 3 minus 2 iota. Express u in the form x plus iota y, where x and y are real. So we're going to find complex conjugate of the denominator and then rationalize it. So for part B, let's rationalize it. 7 plus 4 iota upon 3 minus 2 iota times 3 plus 2 iota upon 3 plus 2 iota. Okay. In the denominator, we're going to apply a squared minus b squared. Okay. Which will become 9 minus 4. So that's 9 plus 4, which is 13. Okay. Show you're working on the side somewhere because there's marks for that. So on the side, you can write 9 minus 4. Okay. And in the numerator, let's multiply them together. 21 plus 14 iota plus 12 iota and minus 8, because iota square is going to be minus 1 and 4 times 2 is 8. So we're getting 13 plus 26 iota, which becomes 1 plus 2 iota after simplification. Okay. That's B part 1. Next is sketch an Argand diagram showing the points representing the complex number u. Show on the same diagram the locus of complex numbers u such that modulus of z minus u is equals to 2. All right, so first thing we need to do is plot the complex number u on an Argand diagram. Let's get started with that. So this would be 1, and then 1 here, 2 here, so roughly here. This is the complex number, 1 plus 2 iota. Okay, we also have to show real part and imaginary part. So this would be x, and this would be iota y. So must properly label the x's. Okay, next it says to show or to plot this. Now, what is this? This is a circle whose center is u and radius is 2. So u is already plotted, so we already have the center, and now we're going to draw a circle with a radius of 2. So this would be 2, and there would be another point here. So no, in fact, the radius is 2, so it needs to go till 3. Okay, so that's 2, and that's 3, so it goes till here. Then here it goes to 0, -1, and -2. Roughly here. And then it will go to 3 and 4 here. And then 2 down would be here. So this circle has a radius of 2. Very bad looking circle, but hopefully you'll do a better job. Oh, no, I made a mistake towards the left. This would be 2. So I'll stop here. This would be a radius of 2. Okay, now it would hopefully look better. So circle with center at U and a radius of 2. Yeah, that looks a lot better. Okay. So that's done. And do we need to do shading, or is it just equals to? No, it's equals to. All right. So next part is find the greatest value of argument of z for the points on this locus. Okay. So locus of points mean that our complex number can literally be any point on this circle. But now, in the last part, they're asking us to choose that point that gives us the greatest argument. So out of all the possible points on this Argand diagram, on this circle, which point will have a greatest modulus? Not this one, because there are more points that have bigger modulus like this one. But this point has even a bigger modulus. This point has even a bigger modulus. So what we do is the greatest modulus is going to be right here. This one. This one would be the greatest modulus. Oh my, sorry, I'm very sorry. We make modulus from the origin. So we make the modulus from here. So like I said before, this isn't big enough. So we don't choose that point. If we choose this point, this isn't big enough. There's a modulus that's even bigger than this. So for that, what we do is we start from the origin and we look for the greatest modulus. A point here would have a greatest modulus. So this complex number will have the greatest modulus, where this line is tangent to the circle. Okay, now we need to find the value of this greatest modulus. What we know is that radius is equals to 2, and we know that radius and tangent are perpendicular. Then we know that this point is 1, 2, and this point is 0, 0. So find the distance between these 2 points, 2 minus 0 whole square plus 1 minus 0 whole square under root. That's a square root of 5. So this line is going to be equals to square root of 5. Now we will be using a bit of trigonometry here. We need this complete angle, this full angle. All right. So we can also make this line, and that's also radius of the circle, which is 2. So what we'll do, we'll find this angle separately and then this angle separately using SOHCAHTOA law and add them together and get the greatest possible modulus. All right, we also know that this is also a 90 degrees triangle. So let me draw this triangle separately for convenience. So this is 2, that's under root 5, and that's a 90 degree, and we're going to find this angle. So we're going to use sine theta is equals to opposite over hypotenuse, or theta is equals to sine inverse 2 upon under root 5, whatever that is. Okay. Next, we're going to use the other triangle, which is something like this. Okay. We know this is 2 and this is square root of 5. And now we need this angle, which is going to be opposite over hypotenuse again. So sine theta is equals to, they're actually both the same, 2 over under root 5. So theta will be the same, sine inverse under root 5. This is supposed to be under root, and then we double it and get the required argument, greatest possible argument. Let me see, did they ask for the answer in degrees or radians? No, they did not. So you can give answer in either degrees or radians. So I will be sticking to radians. So we're going to do 2 times sine inverse 2 upon under root 5, because both the triangles give the same angle. So this would be 2.21 something. Let me check, 2.21429, and that is the answer in radians. So we may rewrite it as 2.21. In 3 significant figures, it's just going to be 2.21.